I'm Professor Brad Fulton, and welcome to my Stats podcast. This is an edited audio recording of my course. Each lecture is its own episode, and there's a total of 24 lectures. This course provides an introduction to the quantitative methods social scientists and data analysts use to collect and evaluate empirical data about society. Through this course, you will learn to gather, describe, and analyze data with an emphasis on the application and interpretation of these methods. This course will also help you to be a more informed and critical reader of academic research, public opinion polling, and advertisement claims that present statistical evidence. Although some of the current events I reference might be dated, the content is timeless. I hope you enjoy this lecture, and if you have any questions, you can email me at bradrfulton@gmail.com. Hi, my name is Professor Fulton. If you like this podcast, you'll love the book I use for the course. It's titled Statistics, Unlocking the Power of Data. This book uses a highly intuitive approach to help students visualize statistical concepts, which accelerates understanding. I've reviewed dozens of textbooks, and Unlocking the Power of Data is hands down the best one out there, mainly because of its unique intuitive approach and straightforward explanations. You can find a link to the textbook in the show notes, and if you use the promo code BLOCK5, you'll get a 10% discount. Yesterday, or on Friday, we looked at the process called ANOVA, which was analysis of variance. What we covered on Friday was if you have a categorical variable and one quantitative variable, and you want to see how the means of each group differs, ANOVA, using the F statistic, would let us know that, hey, one of these groups is significantly different from the other groups. But that's all that it told us. And so today what we're going to look at is multiple comparisons of seeing what specific groups are different from each other. Inferring difference in means using ANOVA. Probably a week or so ago, we did inferring difference in means using the t-test. Remember the t statistic? So this is doing the same thing, inferring difference in means, but using a different method called ANOVA. So in the last lecture, we learned how to test for a difference in means when the categorical variable has multiple categories. So like with the race example, we had white, black, Hispanic. Specifically, we used ANOVA to test whether at least one group mean was significantly different from the rest of the other group means. And today we'll learn how to use ANOVA to identify which of the group means differ significantly from the others. It's not particularly helpful just to know, hey, one of the groups is different. You want to be able to identify which group. The example we're going to use throughout this class is cost of textbooks by field. So does the cost of textbooks differ by academic field? So if you're a science major, are you going to spend significantly more money in textbooks than a humanities major or social scientist? So data was collected on 10 courses within each academic discipline, and they looked at the total cost of textbooks for each course and then added them up, and here's the data. And the reason why I'm showing the box plot is so that you can become familiar interpreting a box plot. It's not the easiest, most intuitive thing, but you should be familiar with what the different characteristics mean. And so this little bullseye here is the mean for each of the things. So this is for the arts and what textbooks cost, and so then the mean value is about $100. And then we can see natural sciences is up to over $150. But then the box plot also lets you know how much the different costs for each category vary. Another way of looking at, which we're more familiar with, is just by getting the summary statistics, which gives you the sample mean, the sample standard deviation, and the sample size. The problem with just looking at these numbers, it doesn't give you a sense of the distribution of the data. And so by looking at a box plot or a bar graph, it lets you see natural sciences seems like it's out in front of the rest of them. The spread by field seems relatively equivalent. Anyways, here's two different ways of providing summary statistics. The question is there a significant difference in the cost of textbooks between academic fields? And this is what we did on Friday. Just the general question, you have a categorical variable, which is academic field. There's 4 categories. And then we have one quantitative variable, which is the cost of textbooks. We want to know, does any of the mean cost of textbooks differ significantly by field? We take all the information from our summary statistics, take our data, plug it into the computer, and this is the output that we would get. So it's going to be the ANOVA table. There's two sources of variation: from the actual variation that occurs by field, and then variation associated with error. Then we have our degrees of freedom, and then the sum of squares, which is the sum of the square deviations, and there's that long formula. You don't necessarily need to know the formula, but you need to know what it's communicating. It's how much does the individual values deviate from the mean values for each group. And then you take the mean square, which is the sum of squares divided by the degrees of freedom, and do that the same with the error term. The final output that we get is the F statistic 4.05. What would you do with this information to answer our question? It says, is there a significant difference in the cost of textbooks between academic fields? And our F statistic for the ANOVA analysis is 4.05. What would we do with this information? Brittany? Stat key. Okay, we're at stat key, and then what do we do? Click F. Okay, so then degrees of freedom, the top will be the degrees of freedom for academic fields. The formula for that is K minus 1, which is number of groups minus 1. So 4 groups minus 1 is going to be 3. And then for the denominator, it's the total sample size minus the number of groups. So total sample size was 40, number of groups was 4, so 36. So we put in the degrees of freedom, and we have our F statistic, and what type of test will we do, or what will we do next? Right tail?
P-value?
Yep, how would we get the p-value?
Change the bottom one.
And it's 4.05. We plug in our observed F statistic, and we see what is the probability of getting an F statistic as extreme as 4.05 when the null hypothesis is true. And so we see that it's about a 1% chance of getting an F statistic as extreme as our observed F statistic when the null hypothesis is true. So our null hypothesis was that the mean value for textbooks across groups, there is no difference, they're all the same. And so then this F distribution is a distribution of values when the null hypothesis is true. We had an observed F statistic of 4.05. That would tell us to reject the null hypothesis, because there's only a 1% chance of getting an F statistic that large under the conditions of the null hypothesis being true. So we can reject the null hypothesis and conclude that one of the fields has a mean textbook value that significantly differs from the rest. Up until this point, it's a repeat of Friday. P-value is 0.014, and then we can make the conclusion that we have strong evidence that the cost of textbooks differ by academic field. Well, which groups, which of the academic fields is significantly different? As sample sizes get larger, you can't just do it visually, but you want to be able to do it in a way where you can quantify. This one is clearly statistically significantly different from the rest. So ANOVA tells us whether there is a significant difference in means, but it doesn't tell us which of the group means differs significantly from the others. From ANOVA, we know that at least one group mean differs significantly from the other group means, and so we can use information from ANOVA to identify which group means differ significantly from the others. So it's taking the ANOVA table and using that information to begin to identify which groups significantly differ. So you start by saying, well, what is the mean cost of textbooks? The way that we would answer this is using a confidence interval. We would have a point estimate for the mean cost of textbooks for the natural sciences, and then we'd want to know the confidence interval for that mean cost. The next question we would ask is there a significant difference in the mean cost of natural science textbooks and humanities textbooks? Because humanities was the one that was the next highest mean value of textbooks. The way we'd answer this question is using a hypothesis test. It's the same grid that we've been working throughout the course, is confidence interval and hypothesis test. It's going to come up again here, so at least there's familiarity in what we're looking at. Before, both of these questions could be answered using either a simulation procedure, where we did bootstrapping for confidence intervals, and then for the hypothesis test we did the randomization process, Or we can answer both questions using formulas based on theoretical distributions, where we have the z statistic, the t statistic, the chi-square, those three. We could answer this question from everything that we've covered before using either simulation procedure or formulas based on theoretical distribution, or we can use ANOVA to make inferences about the population. And you can triangulate to say, we should be getting the same answer because we're asking the same question, but we're just using a different procedure. We're going to use information from ANOVA to make inferences about the population, to basically answer the confidence interval and the hypothesis test question. The main facet of this process is recognizing that the standard deviation is more or less equivalent to the sum of squares. Standard deviation is what we've been working with, and now with ANOVA, what we're calculating is the sum of squares, and I'm going to show you how those two are equivalent. So this is what we learned probably in the first week of class, was that the sample standard deviation for the entire sample, this is how we calculate it. You take the mean value for all the values in the sample, and then you look at how each individual value differs from the mean value. You sum all of that up and then divide by n minus 1 and then take the square root of that. So that's the formula that we use. That's how you calculate standard deviation for any sample. It's the square root of the sum of the variation in sample values divided by the degrees of freedom, n minus the number of groups. And if you're looking at the whole sample, the number of groups is just 1. So this is how you would calculate sample standard deviation. As a reminder from what we covered on Friday, calculating the sum of squares due to error, instead of the whole sample, you're looking at individual groups. So you're looking at, say, natural science textbooks, humanities textbooks, arts, and social science. With the first group, you take the sample mean for natural sciences, and then you take each individual value, the value of textbooks in the natural sciences, and you find out how much it differs from the sample mean, and then you square that, and you do that for each group, and then you sum it all up. Just by looking at these formulas, would you say that these two are equivalent? Or what would be, what do you, if you're kind of looking at the components of both formulas, what would you see? So this one is taking all the sample values, comparing each of them to the sample mean, and then adding them up. So if we look at this picture, sample standard deviation is doing this, and it's saying, okay, here's the sample mean for the entire sample, and it's looking at the deviation across the entire sample. Whereas sum of square due to errors is just doing the same thing but broken up into each of the groups and then adding it together. Two slightly different ways the spread of the data. And the main difference is one is just doing it by looking at the whole sample, and the ANOVA process is doing it by looking at it by individual group. And the reason why it's not exactly equal is the sample mean is going to be different from each of these individual group means, and the degrees of freedom that we're working with changes, because now we're looking at 3 or 4 different groups, whereas with sample standard deviation we're just looking at one group. This isn't just a mathematical exercise to say, hey, do we get the same answer? We actually can use this information to make a better estimate about the population. So then how do we do inference using ANOVA? If the ANOVA assumption of equal variance across groups is satisfied, we can use the data from all of the groups to estimate the variation for specific groups. The ANOVA assumption is that the variation of each individual group is equivalent to each other. Remember in the box plot, it shows the spread of data by academic field. And what that showed you was that each of the groups had the same spread as each other. And so we estimate that the standard deviation for the values in group 1, group 2, 3, and 4 is about the same. And this is important for when we do inference. If the standard deviation is approximately the square root of MSE, and if the sample values for each group have approximately the same variation, then the standard deviation for any group, S sub j, is going to be approximately the square root of MSE. And then this value can be used to estimate the standard error. When we're doing confidence interval and hypothesis tests, the critical value that we're needing to obtain is the standard error. This gives us a way to estimate the standard error. using information from ANOVA. If you remember, when we do analysis for single means, the standard error is the population standard deviation over the square root of n1. And a week ago, we said that the population standard deviation is equivalent to the sample standard deviation, because that's saying the sample is a random sample of the population, so the spread of values in the sample is going to be equivalent to the spread of values in the population. So then the next step that we're learning today is that the sample standard deviation is going to be equivalent to the square root of MSE divided by the square root of n1. Then we can arrive at this as a formula for calculating the standard error. This first step here is what we learned a week ago, and what we're learning today is another way to estimate the population standard deviation by using this formula. So then which approach provides a better estimate? And it's based on which approach gives you more information to work with. Ultimately, it's the ANOVA process that gives you more information, and so the more information you have, the better estimate you can make. Similarly, the equation for calculating the standard error when you're working with difference in means is this equation with sigma 1 squared over n1 plus sigma 2 squared over n2, and that we said was approximately equal to just taking the sample standard deviations for group 1 and group 2. What we've just derived, that the standard deviation for each group can equal the square root of MSE, we can plug that in and get this new equation. So we go back to our original question, which was mean cost of natural science textbooks. And this is going to be the confidence interval for the point estimate. And so this time, just to change it up, I'm going to say, what's the 90% confidence interval for the mean cost of textbooks? And so we have the same formula, sample statistic plus or minus T star times standard error. But now what we're changing is, for standard error, we're estimating it using our new estimation for standard error. And when we're using this as our estimate for standard error, it's going to change what degrees of freedom we use. And we use the degrees of freedom from the sum of squares due to error, which is n minus k, which is total sample size minus the number of groups. If we want to know what T star is, how would we do that? We know what the mean cost of textbooks for the natural sciences is. ANOVA will tell us what the square root of MSE over the sample size of natural science textbooks. And so the one value that we don't know is T star. How would we get that? Stat key. Okay. And then what? T, degrees of freedom, 36. So we're doing a confidence interval, so we want to know what the lower and upper bound is. Two-tail. Okay. And so then what's our T star going to be? For a what % confidence interval?
You said 90, right?
Yeah, so you change it to 90 because you want to know the middle 90% of values. The T star would be 1.688. So that brings us to this formula, and the 170.8 is the mean cost of textbooks for the natural sciences. 1.688 is what we calculated from stat key, and then the 2,536 divided by 10 is what we get from the ANOVA output. And that's similar to what you guys did with the assignment that was due for today, was looking at an ANOVA output and knowing where all the components are. The ANOVA table is a standard table, so you can look at each column and say, I want the MSE, so you can go to that part of the table and get it. And it gives us the confidence interval for our point estimates. So we have a sample of natural science textbooks, and we have the mean cost of those textbooks. And we want to make inference about the population of all natural science textbooks. And so we're 90% confident that the mean value of natural science textbooks is within the range of 143 and 197. If we just walk through the formal way of doing it, we have 90% confidence interval, same formula. And the formula that we used before was using just the standard deviation for the group of natural science textbooks. And when we do it this way, degrees of freedom is n minus 1, which is the sample size for that group you're looking at, minus 1. And so you'll notice that the degrees of freedom is different. And this is where, when I was talking about what procedure gives a better estimate, this one up here gives a better estimate because you're using more information you're using information from the entire sample of 40 textbooks to estimate the standard error, whereas this one, you're only using the information from the 10 natural science textbooks. And so that's why the degrees of freedom is 9. What this process is showing you up here is a way to estimate the standard error by pulling in more information. So if we're saying that the standard deviation of sample values for textbooks is basically the same across every group, we can use information from the entire sample to estimate the standard error for the natural science textbooks, whereas in this way of doing it, we can only take information from the natural science textbooks to make our estimation. Either way you do it, the confidence intervals that you get are more or less the same. But the first method produces a narrower confidence interval because it possesses more information about the deviation of sample values. And actually, a narrow confidence interval is a better thing to have because you can make a more confident estimation of the population parameter. The next step that we would do is the hypothesis test, where you say, what's the difference in mean textbook cost for the natural sciences versus the humanities? And so is there a significant difference in the mean cost of natural science textbooks and humanities textbooks? So this is a question that we're ultimately wanting to get at with this procedure. So the null hypothesis is that the mean value of textbooks for the natural sciences equals the mean value of textbooks for the humanities. And the alternative hypothesis is that the mean value of textbooks for natural sciences are greater than the mean value for humanities. We're going to use the t-test because it's for difference in means. The thing that we're going to be estimating differently is the standard error. The sample statistic here is x bar, the mean value of textbook for natural sciences minus the mean value of textbooks for the humanities, minus the null value, which is 0. What we substitute in is the standard error estimated from the ANOVA process. And again, we have all this information is known. This is from the summary statistics, and this is from the ANOVA output. And so we get a t-statistic of 2.24. Okay, so we want to know what's our alternative hypothesis. The right tail, and it was 2.24. So then we get a p-value of 0.016. It's basically saying it'd be very rare to get a t-statistic of 2.4 when the null hypothesis is true. So we can reject the null hypothesis and accept the alternative hypothesis and conclude that the mean cost of natural science textbooks is greater than the mean cost of humanities textbooks. To show you how this relates and see how they're equivalent, I'll walk through the process that we were doing a week ago. The difference is how we're estimating the standard error. The numerator is the same, and it comes out with a t-statistic of 2.11. The difference with these is the degrees of freedom. The degrees of freedom is dependent on what information you're using to make your estimations. And so with this, you're only using the standard deviation from the individual groups. And so that's why the degrees of freedom is going to be less, whereas this is using information from the entire sample. If we went on to StatKey and plugged in 9 degrees of freedom in the t-distribution and saw how many values were as extreme as 2.11, the p-value that we would get is 0.032. These are different values, but the same decision. You still would reject the null hypothesis. And in most situations, you're working with a much larger sample size. And as the sample size increases, these two will become more and more close. If you have a small sample, then you'd want to use this process because you can work with the entire sample versus looking at just individual groups. You could use either process and still get the same outcome. That was just for 2 groups. We looked at natural science textbooks and humanities textbooks, but there's a bunch of other combinations, like are the mean value of arts textbooks different from social sciences and stuff. Technically, you could individually go through all of those comparisons, and that's what pairwise comparison is, for a difference in means between each pair of groups. You'd only conduct a pairwise comparison if the overall ANOVA is significant. The first thing you need to do is test, do any of the group means differ from each other significantly? And if they do, then you want to do this test for each pair of group. But if there's lots of categories, the number of possible pairwise comparison groups grows quickly. So some of you, for your final project, you selected a categorical variable that has like 12 categories. I think it's religion, has 12 categories. And so once you have that many categories, you're setting yourself up for having to do lots of extra analysis. And so a lot of times what's done is you can collapse some of those categories. So like the religion one would be a good one, where there's about 6 categories that only have 1% of the population is in that category. And so what you could do is collapse all those into one category and just call them other. So then you would have fewer groups that you're working with. If you just want to compare white people to non-white people, you can do that as well. And so with the variables that you have, you're given sometimes more information than what you really need, and you can recode the variable to be what you really want to measure. Also, when you do pairwise comparisons, the process can be automated using statistical software. So you can just plug in all of your groups and the quantitative variable that you're wanting to compare it against, and it'll give you an output of here's group 1 compared with group 2, group 1 compared with group 3, and so on. A week ago we looked at, just by going to religious services, is that associated with being more happy? You could also look at it, does your level of happiness differ by the type of religion that you are? Are Catholics more happy than Jewish people, and so on? Before, we had to take a quantitative variable and correlate it with another quantitative variable and see what the relationship was. This allows us to take a categorical variable and compare it with a quantitative. In your analysis, you have a dependent variable that you're looking at, what affects it, and you want to know what quantitative variables are associated with it, but also what categorical variables are associated with it. So we're, in a sense, building our toolkit needed to do our final project. Let's talk about the final research project. The best way to set up the research question is coming up with something in society that you're interested in. So whether it be income or happiness or attitudes about something, you want to identify the social phenomena that you're interested in analyzing. With the paper that I had given as an example, the key phenomena was HIV/AIDS programs. I was interested in which congregations have the programs and which ones don't. But I wanted to know what were the characteristics of congregations that influence whether or not they had an HIV/AIDS program. But my central focus was HIV/AIDS programs. So there's 3 primary types of categorical variables. There's the ordered, which is if you have a continuum of values, so like happiness or whether or not you should help the poor. Those can be treated like quantitative variables. So you can do correlations between an ordered categorical and a quantitative variable, because for correlations you need 2 quantitative variables. With binomial, nomial means name or category. A binomial is saying it's a categorical variable with only 2 options, and it's usually like gender or yes, no. So there's only two options. And with those, you can also do a correlation, because it's saying if you go from category 1 to category 2, does that have a relationship with your quantitative variable? The third type of categorical variable is nominal, and that's where it's saying you have distinct categories that are not ordered in any way. So like religion would be clearly a nominal categorical variable. You have Protestant, you have Catholic, you have Jewish, you have Hindu, and it's not ordered in any way. They're just distinct categories. And so I think some of you had done a correlation between religion and, let's say it was happiness. And you found, hey, wow, there's a strong correlation between religion and happiness. If you think about it, what it's taking is the values in your categorical variable, which is just I'm Catholic, I'm Jewish, I'm Hindu, and it's trying to correlate it with levels of happiness. But what does that mean? It doesn't tell you whether it's the Catholic people or the Jewish people are more happy or less happy, because religion is not on a continuum. It doesn't mean like if you're more towards the Christian side, you're going to be more happy. So you can't do correlations with nominal categorical variables. What you can do, and what we did do, is looking at how each of the categories differ from one another. So you could take the mean level of happiness for all of the Protestants in the sample and compare that with the mean level of happiness of all of the Jewish people in the sample, and compare that with the mean level of happiness for all of the Hindus in the sample. And that's why, for some of you, I said if you're doing something like religion, for your own sake, you might want to collapse some of the groups so that you're not having to make all these comparisons. When I asked you guys to give me the summary statistics, putting it in a form that, like, providing the units, put out what it's actually measuring. Oh yeah, so also a lot of you had, with your categorical variables, you were giving me the mean value. So like for religion, you said the mean value is 6.2. And again, I'm like, for religious affiliation, what does a mean value of 6.2 mean? What I'm really interested in is what's the proportion of people who are Protestant, what's the proportion of people who are Catholic. GSS or any software will give you a mean value because, associated with Protestant is a value of 1, and associated with Catholic is a value of 2, and associated with Jewish is a value of 3. But the quantitative value for that is meaningless. And so with categorical variables, you're more interested in, even with like help poor, there will be a mean value, and that's somewhat helpful because you can say on average people are more inclined to want the government to help the poor, but what we're also interested in is what proportions say government shouldn't help at all, what proportions say, and I'm going to push you to spell it out because in the final paper you're going to have to say it. You can't just say the mean value for helping the poor is 3.2 because someone reads it and they'll be like, what are you talking about? All right, that's all.